All right, so welcome everyone, welcome netballs. So today we have our speaker is Lin Sun from Queen Mary University of London, and the talk is message passing approach to epidemic tracing and mitigation with apps. And so Lin, the room is yours.
Okay. Thank you, and let me start my talk. I'll briefly introduce to you this project in the first part of the talk, and I would try to avoid the mathematical details and trying to give you an overall picture.
Han, before you continue.
I'm not seeing the slides.
Oh.
Yeah.
Well,
Okay, let me, I think it might be because of, sorry, let me try again. Check my desktop. And how about now?
Natural.
Can you see the full?
Yeah.
Okay, that's great. So in the first part of the talk, I'm trying to give you an overall picture about this project without this very detailed derivation, because for me, I think maybe the second part of the talk would be more interesting. So let's see. So let's start the first part first. So a message passing approach to epidemic tracing and mitigation with apps. And this was a collaboration with my supervisor, Jeanette Stripping-Cody, and two external collaborator, Giacomo Rapsody and Alex Serenas. So the idea behind this project, the project is mainly motivated by this COVID-19 pandemic, because during the pandemic, people are using mobile apps to help with contact and tracing to control this pandemic. So here is a popular mechanism that has been used in many contact tracing apps. So the key idea is like this. You can install a mobile app on your phone, and this mobile app can send some signals. So when two people meet and both of them have this app on their phone could exchange a key code using, for example, Bluetooth or some other techniques to exchange a key code. So when A become infected, one person become infected, and he can update his status in the app. So this app will automatically send a message to B saying, B, you have been in contact with someone infected. So you should isolate yourself, prevent the further propagation. So this contact tracing app is helped to find this potential infected individual before the symptom shows, because the virus can spread between the symptom shows. So in this work, we're trying to theoretically model this epidemic spreading process with this contact and tracing app, and I want to know how effective is this app, or how does this app could affect this spreading process. So here is some basic setting of the model. So we consider a network with n individuals, and clearly the link between these individuals will be the contact. So if two individuals has been in contact with each other, we put a link. If no, there's no link. And there are two types of individuals in the group. So the blue ones denoted they don't have the app on their phone, and the yellow one means they have their app on their phone. And here we assign them a variable called ti equals 0 or equals 1, and I is a label of the node or the individual. So later we'll use this ti, this variable in the equation. So we put it here. And here I would like to show this epidemic spreading process with contact and tracing. There's a abstract from the real process. So in this case, we consider this spreading process. So if someone is infected and this person with the app, which is the first node, so it's infected, the red shadow, and with the app, with the phone. So next step, he could infect his neighbors in the network with a probability P, which also called transmissibility, and this depends on the property of the virus, as well as, for example, the mitigation approach, like self-isolation, etc. So basically, there are many things could affect this transmissibility P. And a next step, clearly, these two neighbors will be infected. So the difference of next step is actually because both individuals, this first person and the second person, both of them have the app. So when the first person report has been infected in the app, the message will be sent to this person automatically. Here we assume like the message can be sent instantly. There's ideal approximation. So he will know he might be infected. So he will isolate himself. So he cannot pass on the virus to his neighbor. But for the second person, for this person, he does not have the app on their phone. So he cannot receive the message from the first person saying, I'm infected. So he could continue the propagation to his neighbors until the symptom shows. So this is a second step. Due to self-isolation, the pandemic stopped at this node, and it could pass on in the second node for the second case. So his neighbor could also be infected. And the other situation is if the pandemic starts with someone without the app, then clearly the first step, their neighbor will be infected with the probability P. And next step, none of these two neighbors will receive any message from the first person because he does not have the app. So they can only know they're infected until the symptom shows. And before that, they could continue infect other people. So next step, they can infect other people with probability P. So this is a basic idealized mechanism of this epidemic spreading process with contact and tracing. And we want to mathematically describe this process. So here we introduce the message passing approach. The message passing approach in general is quite useful, and it could be used, for example, in percolation theory or in epidemic spreading, or maybe in the inference and optimization on networks. So let me briefly explain the idea of this equation. So the sigma I to j is the probability that node I spread the virus node j. So it's a probability, and it's ranged from 0 to 1. And in order to calculate this probability, you see on the right-hand side, there are two terms. The first case is if node I have the app. So I can use some of this simple diagram to express. If node I have the app, and if he received a message, or if he is infected by a neighbor with also have the app, then he cannot pass on the spreading because he will isolate himself. So it will not passing the virus on. But if he receives someone without the app, and he could pass on the transmission. So this is basically the first term. And the second term is if node I does not have the app, so he could pass on the virus anyway, no matter which type of individual he is infected by. So this is the idea of this equation. And you see on the left and right side, you both have the sigma defined on edges. So this is kind of a self-consistent equation. And you need to iterate this equation again and again until it converges to something. And that is a stable solution of this probability. And the quantity we are more interested in is actually the order parameter, which is the total number of individuals infected in this group. So you can regard this as a fraction of the infected individual. And so you can obtain this by summing over the probability of each node being infected and divided by n. So this will be the fraction of node infected. And this sigma I, which means the probability of a node is infected can be simply obtained by this, which means if I'm infected, it means at least I receive one message from some neighbor, right? So this is a basic idea. And okay, so there is a way to solve this equation to determine the critical threshold, meaning that when a pandemic, when you have an outbreak of the pandemic, so I will skip this detailed derivation, but the idea is this critical threshold of an outbreak of a pandemic is associated to the maximum eigenvalue of a matrix B, and this matrix B called non-backtracking matrix, and it's modified non-backtracking matrix, and it's given by this formula. So this is how we can use the message passing approach to obtain the epidemic threshold, in the sense that when you have an outbreak. Okay, and if you look at this equation, you see this equation requires a perfect knowledge of this TI and the network structure, because we need to define the message on the network. So we need to know exactly what the next network structure is. And also we need to know TI, because clearly TI is in the formula. TI is equals to 1 if the person has the app, and TI equals 0 if the person does not have the app. So we need to have perfect knowledge of these two pieces of information. And in reality, or in a more general case, sometimes we don't have the perfect knowledge of TI. So for example, we don't know who has the app, who doesn't exactly. And here we can make some assumptions saying we know the average probability of a node I having the app. So we make an assumption that this probability, the average probability of having a node having the app, is a function of degree. So for example, for a person with higher degree will more probable to install this app. So this is a clearly approximation, and there are some reason behind it. First of all, theoretically, this approximation introduces the least information. We only need the structure information, which is the degree, but not any extra information. And also it makes some sense, for example, in a city, if one person is contacting with everyone, for example, some people working in public service, and he should care more about his health, so he maybe have a higher chance to download this app, etc. So with this approximation, the message passing equation introduced previously can be approximated. So we can obtain an average version of the message passing equation. So we can use this a similar way to find the critical threshold. And if we don't even have the perfect knowledge of the network structure, and we can further do the approximation saying we consider this is an assumption over the uncorrelated network ensemble given by with a degree distribution pk. So we can further simplify or average the message passing equation, and we get this form. The good side of this set of equation is we can analytically solve this critical threshold PC, and is given by this this following formula. So we can analytically predict the critical threshold. So it means that if P, the probability, the traceability is higher than its PC, you will have an outbreak of pandemic in this network. If P is below PC, you will not have a large outbreak. So this is the basic version of the theory. So using this model, we could able to predict the critical threshold if I know, for example, degree distribution, if I know this relevant information. So the next step we are doing is the optimization. So we already know how to calculate the critical threshold, but we want to know how we can optimize the critical threshold under certain constraints. For example, in the population, the app is only available to a certain fraction of individuals. So this is a reasonable assumption. For example, someone don't want to install this app, or someone don't even have a phone which allows to install such an app, etc. So this is a constraint. I want to know if there is such a constraint, to whom we should distribute the app first to reach the optimal outcome. So we could consider this is this condition is a constraint, and we basically want to maximize this PC. PC is given by this formula. So this is an optimization problem, gives the Heaviside function. So the idea is the optimal solution is have all nodes of degree k greater than the threshold kc with 100% app adoption. So we focus on the people with higher degree first. Of course, this is true under this assumption, which is the T probability of installing an app is a function of degree. Okay. So here is optimal strategy. So we compare this message passing theory with Monte Carlo simulation on several networks. You see the first one is a random Poisson network, and B, C, D are some real networks. So this is a friendship network from DISA in 3 different countries. And so the blue dots are the Monte Carlo simulation. Here I set KC equals to K, and the K is a very large number. So this means that we don't have app in the network at all. So this is the blue dot just refers to the case, the epidemic spreading without the app. And the green triangle means we have the app, okay? And the solid line and the dashed line are the message passing. So first of all, you can see the message passing agree very well with the Monte Carlo simulation, which proves this theory works well. And you compare this green triangle and this blue dot, you see there is a great improvement on this PC. So PC is when the S becomes non-zero, basically. So that means adopting an app in the population indeed is effective to increase the critical threshold, in other words, to mitigate the pandemic. And on the other, so we further explore the optimization problem, or in other words, we further explore the improvement on PC. So we want to compare with other strategies and how it works. So we change the expression of the T a little bit, meaning that we can change or we can tune it from the purely random strategy, which means everyone have the same probability having an app, to the optimal strategy, which we mentioned previously, that only the hub node have the app first. So we can compare the different strategies, and on the right-hand side, you see we plot this phase diagram. The x-axis is rho, which is the level of random adoption of the app in the population, and the y-axis is the critical threshold PC. So you see clearly, if you increase rho, if you have more, have a higher chance of random adoption in the whole population, you have a higher critical threshold. That's no problem. And also, if you decrease KC, I mean, KC is a threshold when of which above KC everyone has the app. So if you decrease the KC, you will find a dramatic increase of the critical threshold. And we also notice that even if there's no 100% app adoption, the epidemic can still be mitigated in a relevant way, and it's good. So, which means you don't really need everyone have the app to control this pandemic, but as long as, I mean, this line basically gives you an idea how much you need to adopt, how much app you need to adopt in the population to mitigate the pandemic to a certain level. So in conclusion, this message passing theory is able to predict the epidemic threshold in the population adopting and tracing app. By the way, I would like to emphasize again, as this is a theoretical model. So the aim of proposing this model is not really accurately predict to what percentage, which percentage of app we need to adopt in the actual population of the actual pandemic, but in the sense that this is a theoretical model, in the sense we could obtain some insights from the theoretical perspective of how this app adoption could affect the pandemic, because clearly the app adoption affects the pandemic in the nonlinear way, and this theory captured this nonlinearity effect induced by this app adoption on epidemics, right? And under our assumption, which is the probability of adopting an app is a function of degree, then the optimal strategy of app adoption will be targeting high degree nodes. All right, in the end, this paper is been published on Physical Review Research, and the code of the message passing and as well as the Monte Carlo simulation is also available on my GitHub page. So before going to the next session, so first of all, thank you.
Thank you for the talk.
Before going to the next session, I'd like to take any questions if there's any.
Thank you, Han. Have you tried doing everything that you have done, but on a correlated network? So imagine that you have some sort of cliques or any sort of degree correlation in your network structure.
So that can be done. So basically, the message passing, at least not at least, this is true that this message passing equation, as well as this averaged message passing equation, which is here, it does not really relevant to this degree distribution. Either there is correlation or not, the algorithm will work both, as long as the network is locally tree-like. So if the network is not super dense, then it will work. So basically, this algorithm can run on any network. If you give me a network, and I can tell you may not be mathematical precise, but it could be a good approximation as long as the network is tree-like. But the following simplification or this expression, this is not what will not be true on the correlated network. So if on a correlated network, we may need to change this equation accordingly in a certain way. And in that case, you may not able to obtain the critical analytical results of the critical threshold, but it can be generalized.
Okay, thank you.
Any other question?
Okay, then if no,
maybe we can go. Yeah,
if no question, we can.
I have a question.
Okay.
Have you tried also to look at what happened to your model if you have like a time delay?
Yes. Okay. So this is a very important thing if you want to apply this model to real problems. But we haven't done this because first of all, the purpose of this paper is we want to gain some theoretical insight. So we want to make the math of the model simple. So clearly introducing this time delay may result in, we're not able to obtain an analytical result. So yes, this is definitely a way to generalize this model if you want to use it in application. Exactly.
Okay. Thanks.
Oh, by the way, although maybe you could consider, for example, you can consider effective way of introducing the time delay. For example, if you introduce a time delay, it may change the transmissibility of the virus in a certain way. So if you can find a relationship between this transmissibility and the delay, then this model could directly be applied. So just different P. But in general, yes, this is a way to generalize this model in real problems. Okay, so it seems
we can go to the next part.
It's good because it seems we have still have a lot of time. So for the second part, first of all, I'm not going to tell you anything concrete. I just want to bring up this discussion because this also have been a problem that I kept thinking for a while, is how to propose a new research project. So far, so basically, what I'm doing during my PhD is like the project is already almost there. Some ideas or some draft has been proposed by either the collaborator or my supervisor. So I'm mainly working on something more concrete. We know what we're going to do, and we do it and analyze it, whatever. But in the future, clearly, if I'm staying in academia, I will in the end propose my own new research project, maybe from scratch, maybe from the very fundamental level. And I always have this question that how do you propose a new research project? So before I start, there's a disclaimer that the following contents are just my personal ideas and perspectives. I mean, I have a background in physics, so this might come from the more related to physics, and the view is definitely biased and definitely incomplete, and maybe very wrong.
This is a very physical introduction.
So again,
only approximation.
So just want to bring up this discussion, and I hope that you can also share some ideas to this question. So why is this question important? The first I'm thinking is, in the end, as a researcher, I will need to propose my own project. I need to find the route to that, because the idea just not randomly coming up to my mind, but there should be a methodology or should be something to guide you to propose something new. And I think methodology is usually unavailable by reading the paper, because reading a paper is always the paper is always written in a structured way. For example, in a mathematics paper, if you read a proof, you can follow step by step, but that is definitely not the order that the author come up with the proof, right? So the author may say, I need to prove this, and then I need to prove something before, and then something before. In the end, I find a proof. But in the paper, he will write from the very beginning, we have this, we have this, we have this, and in the end, we can prove some argument, right? So for example, when you read a paper, you may not really know where this idea coming from. And you may not really know why you're posing this specific question. I mean, of course, in the introduction of paper, they may provide some motivation of this paper, but this may not be the thing that comes to their mind when they're proposing their project. Maybe in the end, they found this is a good motivation, but may not be exactly what they think at the very beginning. And also, why this method? The paper always tell you that they propose a method and this method work, but why they choose this method? How do they think of this method? I think this is something it's quite difficult to find simply by reading papers. And also, I think there are a lot of interesting questions, but how do you know you're proposing a reasonable question? So you can ask lots of questions, right? I randomly write something down. So for example, I want to find a method to predict the stock market. Okay, everyone wants to do that. And this is a good question, right? If you can solve it, you will be rich. So it's a good question. It's very useful. But how do you know this question makes sense? For example, is this really possible to predict this? Or to what extent it is possible? For example, can you predict what happens to the stock market in 1 day or in 2 days or in 1 hour, 2 hours, etc.? So how do you know? So this is a good question, but you may not be able to find the solution. And the second type is, for example, I want to predict the pandemic. I want to know after the outbreak of COVID-19, after 1 month, I want to know how many people are infected in the world. I want to have a mathematical model to predict that. And there are a lot of questions coming up to us. For example, what I need to make this prediction, what data I need, for example, if this data is available for for working this out, and most importantly is how I contribute to this problem using the knowledge I have. I may have the good question, but I may not have the tool to solve it. So these are all problems. Even you can propose an interesting question. So if you cannot solve this problem, the question will always remain as a question. It cannot be converted to a paper or to and to make progress. So these are some questions I personally have. So and previously I have been discussing this topic with my supervisor and with some other people, and I try to summarize some of my idea. So the idea is, when you solve a problem, or when a problem is solved, you can classify this in you can consider a simple process. So first you observe. There is a theoretical observation. There's observation, or the question comes up, and you want to solve this question. So you propose a model, or you just propose a theory. So a model is maybe some assumptions, etc. And you develop this model in a complete theory, and then you solve the problem, right? This is I think my impression is, in physics, this is a more common way and reasonable way, and I provide some examples. For example, the observation, the question, maximally experiment. So you find there's no ether, so for light to travel. So it's disprove the existence of a what is it? The thing you need for the light to travel, right? And so this introduced a problem, right? So the classic mechanism not work perfectly at the speed of light. So here comes the model, which is you make some assumptions, laws of physics are invariant, and speed of light in the same in the odd coordinate system. And then you develop from these assumptions, you have this special relativity, right? So of course, the real situation is definitely much more complicated than that, but it's a possible route. So we have a problem first, and we have a hole in the theory, we have a problem in the theory. So we make some further assumption, and we develop a new theory to solve the problem, right? And also, for example, in the ultraviolet catastrophe or the photoelectric effect, this is your observation, which cannot be explained by classic mechanics, classic physics. So assumption is made, energy quantization, and you develop this into a theory, which is quantum mechanics, right? So these are some examples from physics. And maybe there are also some examples from the other area of study. For example, the question is text recognition. I want to use some algorithm to recognize a text. So this is a very well-defined question, right? And I consider a model. For example, I consider the message passing, machine learning framework. We use a machine learning algorithm to solve this question. And further, we may be able to develop a theory of this machine learning framework. For example, why this works for text recognition, or there are many theoretical questions related to the machine learning algorithm, right? And for example, also we could ask how to predict the pandemic, and we can develop model accordingly. Considering what we have, what we want in the end, and then we can develop the theory. For example, the SAS or SAR, or this the agent model of epidemic spreading, and we can develop a theory on the top of this model. So this is a route. So I call it top down. So top is basically the question is on the top, and the theory is the underlying thing. So you have the top first, you have the question, you have the observation, and you go down to the theory. So we call it top down. So I summarize, there are some properties, or there are some characters of such way of proposing new project. So usually the question is very clearly stated, right? In these examples, I know exactly what I want to do, or I know exactly what the question is, right? For example, my question is why this classic physics model fail, the theory fail, and what can we do to make the theoretical prediction agree with the experiment result, right? So the question is usually clearly stated. And the very difficult part is the plausible method is usually unknown, and there might be infinite number of candidates. So you may choose method from everywhere, and you just want to solve this problem, and you don't really know how to choose method, or you don't know which method could eventually solve the problem. And the third observation or third character might be true, which is sometimes fully solve the question might be impossible or too complicated. And if you want to get a good result, the analytical results are usually not available. So for example, you want to accurately predict the pandemic. You want to know how many people are infected after a month. I know there are papers that people using like a machine learning algorithm to help with this. And if you can make the accurate prediction, you may not always obtain a very analytical result. So mathematically, it's maybe you don't like a black box. Sometimes you don't know what happened inside. And if you finally work out this question, the outcome is a developed model or developed theory could usually directly help solve the question. I mean, that makes sense because you develop the theory for this question. You want to solve the question, so you develop a theory. So if you have a good outcome, means your theory works, right? So this is one way, which I think the usual way, or in the first 2 years of my PhD, I think this is the only way, right? In physics, almost everything is done in this way. You have a question, you solve it, and good. But my supervisor pointed to me, there could be another way, which is the opposite direction. This is from top down, from top to bottom, but we could also do from bottom to the top. I haven't come up with many examples of this, but there might be more. So bottom up means that we do not have a very clear question at the very beginning, but we work on the theory first. And there is an interesting or quite famous example is the Dirac equation. So the Dirac equation predicts the existence of the positron, so the electrons with the positive charge. Because I'm not know this perfectly well, but it seems that this positron is a solution from the Dirac equation. So you develop the math of the Dirac equation and you found a solution which could means something. And in the end, it is indeed discovered by experiment, although I think it's independently. But this gives an idea of something else, which is we work on the theory first. And the theory itself may guide to some new experimental discovery or to guide a new question. So this is another way. So there are also some features. The questions usually unclear because we start from the theory. We may not have a perfect question to solve. But the good side is method is known because we are extending the theory we already have. And the project usually starts from mathematics, and the math is usually relatively simple, and analytical result is usually available. Because we have a theory and we play with the theory itself. So which means we are not going to make this super complicated, and we may be able to solve it analytically. So this is a good side. And so the third feature is the proposed model or theory may not be able to directly help solving questions. So this is the bad side, but it could provide some insight from other perspective. Because you develop a theory not really aiming at directly solve the question. So you cannot really expect it will, in the end, perfectly solve the question itself. But in the end, the observation of questions might provide a motivation, but the research is not aiming at directly solving the questions or explain the observations, but more like provide an insight. And I believe this project I introduced in the first part is more like constructed in this way. I can show you some. Okay. Sorry. So these are two methods which potentially can be used, and the first one it may be more common, and second one to me is something new, but it could work well. And in reality, maybe we can combine both methods. So we obtain some motivation from the observation, and this gives the motivation to math. Like we know how we can do on the math, and the motivation is provided by the observation. And the mathematics of the theory could be simple. And the outcome may not able to solve the question directly, but may shed some light on the problem. So this project I introduced in the first part is quite, I mean, although this is not proposed by me from scratch, but after finishing this project, I believe this project is more likely to be proposed using the second method. So we developed the theory, we developed the math first, and the math clearly is motivated by the reality. And then we finish the whole model, and it indeed provides some insight on the problem. So for example, the first two equations are something we already know very well. This is the SIR model, and it can be mapped to simple link percolation, and we have the message passing equation for this SIR model and this averaged version. So these two equations we already know very well. And this is the following equation for the SIR model with contact and tracing we proposed in this work. So you see the equations are in a very similar form. Mathematically, they are very similar. You just basically add one extra term, or you add one extra variable, etc. So mathematically, it's simple to extend from the case we already know to this new case. Of course, why we're doing this is motivated by the reality. But with this set of equation, we know how to solve it. We even can expect some result just by looking at these equations. And in the end, this equation, this result indeed provides some insights to the to the real problem, right? Indeed, it does not really fully solve the question or fully can give you a perfect prediction, but it contributes to the problem, right? So it gives you some idea that what happened there. So this is my idea of the proposing a new project, and maybe we could try to use both methods or combine them. And here I show a rough example. So I want to know something else, which I think it could be benefits to all of us. So how do you get new idea of a new project? So maybe people here come from different background, mathematics or computer science, physics, or some other areas. So is there a practical way for you to propose new project or getting new ideas? And the second thing is if there's any difference between the theoretical study and the application study, because what I'm working on is a theoretical study. So this way might work. And on application study, it might be a different case. And if there are some other methodologies. So these are my ideas. And if you have any ideas, we can have a discussion here, right? We still have some time. Thank you very much.
Thank you, Anlin. So is there any question or idea from the audience for this discussion? Because I really think that, for example, for the first question, how do you get new ideas for a new project? I think that there are many answers to these questions. One could be if you read papers and stay updated on the state of the art of your field, for sure you can find some ideas there. But what I found very useful, thanks to the end of the pandemic, is the fact that we are going again to in-person conferences. So I think that staying together and really stay there when someone gives the talk about its research, its project, that could create connection in the sense in your brain for finding new idea for new projects. So I think that one of the possible answer is trying to go to talks also outside. If you are if you are a very like theoretical researcher, I think that a good approach to have this mixed method of like finding application for your theory is to go to more applicative, I don't want to say conference, but maybe talks. Because it happened to me. I was curious about a research in biology about some like bacterial stuff, and I started to talk with the people working on this project, and then we come out with an idea for using my theory in that specific application. Because I think one of the problem of these two parallel but different approach is that we don't have many communication between the two approaches, if you think about it, because sometimes more theoretical researchers are very focused on the theory and not on the application, but it's true also in the other way. So maybe one thing to do could be try to have a communication with the other side, if you want, and help each other like in solving problems. Because yeah, that could be an idea. So my insight is my suggestion is go to the conferences and go outside our comfort zone. So try to connect with people in other different fields.
Yeah, that's quite true. That's I do agree that a in-person conference is much more helpful than the online conferences. I mean, I think some ideas or some for me, some ideas I obtained or this thing that not really comes from the presentation itself, but more likely to happen when have the casual discussion.
Yes. Between presentations.
Yes. So yeah, that's why the in-person conferences are more useful.
But I think yes, that this thing of the mixing the methods that you mentioned, it's really a thing, because maybe you can also, because I think it's really a satisfaction when you produce a theory and then you discover that that theory could help real problems as well, right? So that's a satisfaction if you want.
Yeah, it is kind of interesting because like classically you have a question and you find a solution, and like for this project it's more like I have a solution and then find a question. Yeah, I'm trying to find at least a narrative of this for this theory.
Yes, it's true. It's really unusual, but I think it's unusual for me for sure, because I'm more like a applicative. So I always go in the other direction. But yeah.
That's definitely the other direction. Also, for me, it's quite natural because it's very strange. Because when we write this paper, it's very. I think we already have the framework, have the math, everything, and we're writing. So, what is our motivation? Why we are doing this?
Yeah, but science is also that.
So it's strange, but it could work. Maybe not every time, but it might be a way to think if the other way doesn't work very well. Yeah, is there any other? I think we have some computer scientists here. Is there any?
I don't know. I wanted to say that I agree with Sylvia about the thing about collaboration, because I really, for my experience, I really think that collaborating with other people and sharing ideas really can bring the research forward. And maybe another thing I want to add is that the approach might really change a lot between different fields, because I also think that in mathematics, for example, you just stop at the first step of the scheme you showed us. I mean, that's just theory. And I also think that it's not, I mean, research, I do very much applied research, but there are other fields where they do not think of applying their stuff. And I think, for example, at literary studies or philosophy also. And that's, I think, a very different story from this one, which I'm not familiar with, but I don't know if we are all from the same, like more scientific, in the sense that mathematics, computer science and physics background in here, but I would be curious anyway to know the point of view also of these other fields, because I think that they really do not care a lot about the application. And I think they, no, it's not me who thinks, but it's like their research still goes on in that direction. So, and it's fully theoretical. So that's another point that maybe.
Yeah, maybe we should invite some pure mathematicians.
Yeah.
We can go
Yeah.
and ask.
Yeah, there are many of them in the office. So.
Yeah, I know.
Yeah, I think what I do is more like in the middle. We care about application, not too much. A little bit.
No, I mean, I'm more on your side, but I mean, to my experience, there are also, I know some engineers, basically, mostly, who kind of have their models. For example, they develop their models, and then they desperately find the model to fit the data they're working with, just to like promote the model.
Mm-hmm.
Yeah, that's another thing that people do. I mean, I do not really agree, and I do not see myself in that kind of approach, but that's another thing that sometimes is done. So it's like what I want to say is that maybe, yes, there are other methodologies, so meaning that they're not the two unilateral things that you showed us in the slides, but as you were saying as well. So yeah, that's it. I don't know.
Yeah, definitely. I mean, what I show here is just a very rough idea, and the point is, I mean, and this arrow may always exist like this, not always theory, application, theory, but there might be some other directions, or I don't know much.
Yeah. Also the direction of only applications.
Yeah,
also that direction.
Exactly. So this is a one-dimensional arrow. So the arrow can be in the high-dimensional case.
No, this is true. Yeah, but still, the first point is very annoying. I mean, I think that.
Yeah, it's not easy at all.
No, exactly.
The what?
The
first question, like, how do you get new ideas?
Yes.
That's very.
That's why I want to. Sorry.
No, I mean, that's very hard to answer that, I think.
Yes. That is why I want to bring up this discussion, because later, if you want me to lead a project, so I have no idea what I should do. Like, how do you know you choose the right method? How do you know this way will work? How do you know? And there are a lot of how do you know thing.
Yeah.
So yes. So if there, I'm trying to bring this discussion here, because if there's some guideline for how do you lead a project, or how do you propose it and do it, that could be very helpful. Yeah.
I don't know. I think we'll find out, maybe.
Yeah, I think part is experience.
Yes, definitely.
Part is experience, because you have to try and see what happens. But
yes,
at the same time, I think that I think that a good way could be like to try to have a plan, okay, roughly. and yeah, but it's not really easy to find these important questions. But research is in our field, if you want, in the direction that was, if I remember, top to bottom. So from the question to the theory, you have to find the questions, right? Because otherwise you cannot start your research. So that's not easy at all.
Yes, it's finding a question and finding something you can solve, you can
Yeah.
possibly solve.
Yeah.
Yeah.
But again, if
Definitely
you
very-
go to conferences, for example, I don't know, yeah, our conference in network, for example, the ones in Palma last year, there were so many different fields. You can go from biology to chemistry to health and stuff like that, economy, business, stuff like that. And you can go there and look at what they are looking for. So what are the questions there? And then maybe you can like think about, oh, but maybe I can apply this and this and this to this. Or maybe I know how to solve this problem using mathematical models or stuff like that. So I think that's a good way to go for hunting questions, catching questions.
Yeah, it is true. And I think that this must go together with a lot of study, though.
Yeah. Also.
Yeah, I mean that helps too.
Definitely, you need to read a lot.
Yeah. So maybe we can. Is there any other question or ideas, comments that you want to share? Okay, so I think that we can stop the recording. So thank you, Anlin, again for the discussion and for the nice talk. And yeah, see you next in 2 weeks time.
Yeah, see you.
Bye.
Thanks, Anlin.
See you.
Take
Bye.
care. Bye-bye.